Okay, AP Calc class, we're going to continue on with our 2.3 notes. We're going to look at examples 6 through 10. And starting off, we're looking at the derivatives of the trig functions. We looked at derivative of sine and the derivative of cosine in the previous lesson. And hopefully you remember those. The derivative of sine was cosine, the derivative of cosine was negative sine. The other four trig function derivatives are listed here. Okay, so probably the most common three that you're going to see are sine, cosine, definitely, and then tangent. Occasionally you'll see a secant or or these other ones. And the question I always get is, do we have to memorize these? The short answer is yes, you do. But it's probably best to know that probably the most common ones you're going to see, obviously derivatives of sine and cosine, tangent, secant is, these ones are probably lesser, cotangent, cosecant, but there is a pattern here, and I want you to try to look for that. The derivatives of all the cofunctions, cosine, cotangent, cosecant, those are the ones that are negative answers, okay? The other ones, sine, tangent, secant, those are positive values. And you're going to notice, if you can remember that the derivative of tangent is secant squared, well, its cofunction, the derivative of cotangent, is just negative cosecant squared, okay? So there's like a pattern there. And then this one, the derivative of secant is secant tangent. Well, the derivative of the cofunction of secant, which is derivative of a cofunction of secant, is the same kind of pattern, except it's negative, and then each of these, instead of secant tangent, it's cosecant cotangent. Okay, so I know that's not necessarily real easy to just remember, but if you study them a little bit, that pattern is there. Derivative of tangent, secant squared; derivative of cotangent, negative cosecant squared; derivative of secant, secant tangent; derivative of cosecant, negative cosecant cotangent. Okay, so remember where the negatives go, and then if you can remember this half, I think then this half over here kind of follows a similar pattern. Okay, so the first thing we're going to do is we're going to go through the proof of the derivative of tangent, and we're going to do that because we learned the quotient rule, and we know our trig ratio for tangent is the sine over cosine, right? Sine of x over cosine of x, that is the equivalent of tangent. Okay, so our proof comes through this process. We can use our quotient rule. So if we do the derivative thinking of our low d high minus high d low all over the square of what's below, so I would go low times d high. So derivative of the sine is cosine, right? And then so that's derivative of the top and then times the bottom. Whoops. Times the bottom is just times cosine again. Right? Cosine of x times cosine of x. So that's what I get when I start this thing. And then minus, okay, so that's, think about this, low d high minus, and now we're going to go high sine of x, times d low, what's the derivative of cosine? So that's going to be, derivative of cosine is negative sine. And then it's all over the square of what's below, so all over cosine squared, right? Okay, now take a look how this is going to be. This is going to be cosine squared. So to save myself some room, I'm just going to, this is the same as cosine squared of x. And then this is sine squared, and I'm minusing a negative sine squared, so that's going to be plus sine squared of x. And hopefully you remember this is one of the most common trigonometric identities that we use. This is the Pythagorean identity. Cosine squared plus sine squared is equal to 1. And so then my numerator, cosine squared plus sine squared, is equal to a 1. So I've got 1 over cosine squared of x. And hopefully you remember that reciprocal identity. Cosine is the reciprocal of secant, and that's how this is equivalent to secant squared. 1 over cosine squared would be the same as secant squared of x. So our derivative of y with respect to x would be the same as secant squared. So that's the proof of that one. And you could do secant in a similar way if you set that one up as its ratio identity, which would be 1 over cosine, and then using a quotient rule, I think we could come up with that value when we do our derivative. Same with the others. Okay. So it says find the derivative of each, and what we want to do here is just basically apply the rules that we know. So dy dx. Derivative of x is just 1, and derivative of tangent of x, remember that one? So that's our secant squared that we just did. So it'd be minus secant squared of x, and so that's all we'd have for that one. Okay, and here we've got a product rule, so let's think of this as f of x, and then we've got another g of x here, so those are our two functions. So when we do dy dx, we're going to do derivative of the first, which is 1 times the second, so that would just be, 1 times secant of x, plus, and then it's the first x times the derivative of the second, derivative of secant. Remember that one was secant tangent, and so we'll have secant x tangent x like that. And I don't know that there's a lot. You don't really, and don't think of this isn't distributing, because these are just three things being multiplied. So really it's just secant x plus x secant x tangent x, and that's really all we do with that. Okay, so that's about it. Activity, example 7 has this activity. I'm not necessarily going to go through that one. It's just kind of a, basically they're saying this is a trigonometric identity. If we were to do the derivative of each side, we can simplify and get the same value. I don't think I'm going to spend time with that one. Let's take a look here at the higher order derivatives. This is important. These are important connections here. So they always give you, well, I should say always, but in these problems, what you start with typically is your position function, and they're going to say, that would just be a time versus a height or a distance or something like that. And it's going to be generically labeled as S of t. Position is typically labeled with S of your input value, which is usually time. So S of t is your position function. We talked about this in an earlier lesson, that the derivative of your position function is going to give you your velocity function. So S prime of t is equal to V of t. And remember, when you're taking a derivative, you're finding a slope, right? So if we were just giving a position like meters or something, and then when we find a slope there, we're dividing that, we're dividing our meters, which is usually our y coordinate, by our x coordinates, which is time. So that would give us like meters per second, right? So if this was like in meters, and then, well, now I'm going to do a slope there. I'm dividing by that x coordinate, so that's how I get like a velocity, like meters per second. And then when I do a derivative of a derivative, like a second, it's like a second derivative is what we'd call that. That's called acceleration, because again, we're going to find a slope of a slope already, and so really we're dividing by a time unit again, what if it was seconds or whatever it was, but that's kind of the idea how we're going to get then meters per second squared. That gives us acceleration. Okay, so just some notations. First derivative, y prime, f prime of x, dy over dx. Second derivative, you might see the two kind of apostrophes or prime marks there. So y double prime, f double prime of x. And when it's in this notation, they'll put the little exponent there. So it's the derivative, the second derivative of y with respect to x. Okay? So we're finding that second derivative of the function y with respect to x. And then third and fourth and so on. Like we said, second derivative is called acceleration. So you've got first derivative is velocity, second derivative acceleration, third derivative. They call that, there is a name for that. It's probably something used in physics. We don't really use it. It's jerk, I believe. Fourth, I'm not sure about an application on that, but theoretically we can find those. Okay, so in this example it says we are to, because the moon has no atmosphere, a falling object on the moon encounters no air resistance. 1971 astronaut David Scott demonstrated that a feather and a hammer fall at the same rate on the moon. The position function for each of these falling objects is given by, okay, so this was on the moon. This was our position function right here. Okay, so it says where S of t is the height in meters and t is the time in seconds. So what's the ratio of the Earth's gravitational force to the moon's? That's kind of a, they kind of expect us to know some things here. So something that we do need to know is that acceleration due to gravity on Earth is negative 9.8 meters per second squared. And to figure out the ratio of the gravitational force, what we really want to do is compare the acceleration due to gravity on Earth compared to the acceleration due to gravity on the moon. And to get that acceleration on the moon, they've given us the position. I'll just write s of t to start. So they told us that s of t was negative 0.81 t squared plus 2. So the derivative of that would be, do the power rule, so we'd have negative 1.62, and then that would be t to the first. My constant would disappear, and that would be our velocity, right? That's our velocity function. Now our acceleration, a of t, would be the second derivative of s, which would then just be negative 1.62. It would be a constant acceleration of negative 1.62, and we know that our units in this, well, they told us that this was meters in seconds, right? So we'd have meters per second squared for our acceleration. So when we compare these two values, on Earth, negative 9.8, and on the moon, it was negative 1.62. And if we divide those out, you get like a ratio of 6.05. The Earth's gravitational force would be about 6 times greater. So okay, so our Earth's gravitational force is about 6 times greater than that on the moon. Okay. All right. Example 9. Okay, so it says this is kind of a challenging second derivatives. Many times second derivatives get easier with like polynomial functions because they just get simpler as you go. With trig functions, that's not always the case. So if we're going to do, first of all, y prime of t, so we know that the derivative of cosecant is negative cosecant. Remember to put your variable in there, t, and then cotangent. It's kind of a bad variable because, well, we got t's and, yeah, well, just do your best. And then, so if we're going to do a second derivative, okay, so now what we have is a product. We've got negative cosecant of t times cotangent of t. That's what that's supposed to say. And so we had to do a product rule. So we're going to do derivative of the first. So I'm going to, this negative, you know, it's kind of rides on the outside there. And so the derivative of the first, so the derivative of cosecant is negative cosecant t cotangent t, and then times, leave the second alone, right? Cotangent t. So let's see, try to follow this. So what I did here in my product rule, derivative of the first times the second. So that's the derivative of the first times the second. I just kept that negative there, which is going to end up canceling that. And then plus, and then it's the first, leave that one alone, negative cosecant t times the derivative of the second. Well, the derivative of cotangent of t is negative cosecant squared. So negative cosecant squared of t. Okay? And if we clean that up a bit, this is going to be cosecant t times cotangent. That'll be squared now because there was two cotangents there. And then we're going to have a negative times a negative there, so that would be plus cosecant cubed. And I think that would be the best we can clean that one up. All right. Okay. Last one here, definition of a derivative of an absolute value. So an absolute value function, so it says recall the definition of absolute value from college algebra, which is basically it is like a piecewise graph, right? It's just this simple V shape, right? This is what absolute value. So it's a absolute value of x. So we know that basically it's just two linear equations. It's one that has a positive slope, so it's just y equals x, and then y equals negative x, and it's y equals x when x is greater than or equal to 0, and it's y equals negative x when x is less than 0. Now, if we think of the derivative of this, so if I was going to do the derivative of absolute value of x, right? And if I was doing it in terms of this piecewise function, I would say, okay, well then that's equal to 1 when x is greater than or equal to 0, and it's equal to negative 1 when x is less than 0. It would be like that piecewise function, right? And so what does that look like? That would look like something like this, where I'd have, if this was 1, I'd have a line like going like this, and if this was negative 1, I'd have something going like this, right? And I don't know if you recall this or not, but remember what we had, this graph, if we have like absolute value of x over x like that, you remember that that's kind of what that looked like, only we would have had more probably we'd had an open circle in both spots here. But that's really what that is. It's this graph right here. It's this function. So when you do a derivative of absolute value of x, you can state it as a piecewise like this, but a formula would probably give this as the derivative of absolute value of x. And so in a similar way, if we were going to do the derivative, it says use the definition of absolute value. And if on this one, if we were going to use the definition of absolute value, I would say, okay, well, that means if I would want to use like the piecewise function here, it would be 2x minus 5 when x is greater than or equal to 5 halves, and it would be 2x, negative 2x, technically plus 5 because you put the negative out in front of that. Distribute that through. That would be when x is less than 5 halves. Now why is it 5 halves? Because if you graph this out, your absolute value, that's going to have, it's the equation 2x minus 5, and that it's going to have an x-intercept. The x-intercept is going to be at 2.5, and so you end up with that graph that looks something like that. Okay. So that would be what that definition is. So when we do f prime of x, then that means that we would have, it would be 2 for this part when x is greater than or equal to 5 halves, and it would be negative 2 when x is less than 5 halves, right? And so basically what that would look like is, we would have same kind of a thing like this. We'd have 5 halves here, 2.5, I guess. So right in here, we would have 1, 2, something like a horizontal line going this way, and then we'd have horizontal line. I put one circle, and it would be like going this way here. Okay, and so that's kind of using the definition of absolute value to do that one. But that's it. I think that's all the examples. So mostly the trig stuff, and also the higher order derivatives would be the most important pieces of this second part.